What if I told you that one of the most successful drag racing innovations of the 1970s came from deliberately making a chassis worse? Not stronger, not stiffer, not more rigid, but intentionally flexible, bendy, almost flimsy looking. While every other pro stock racer was obsessing over building the stiffest possible chassis, one Illinois genius was secretly engineering his Chevy Vega to twist and flex like a wet noodle, and it made him unbeatable. Now, before we get into this is legacy motoring, and I spend way too much time thinking about chassis engineering that shouldn't work, but absolutely does. If you're someone who geeks out over drag racing history and the wild innovations that changed the sport forever, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Alright, picture this. It is 1974 at National Trail Raceway in Columbus, Ohio. The staging lanes are packed with the biggest names in pro stock. Ronnie Sox and Buddy Martin are there with their Plymouth. Bob Glidden brought his immaculate Ford Pinto. Wally Booth is lurking with that gorgeous Oldsmobile Cutlass. These are million-dollar operations, factory-backed teams with the best engineers Detroit has to offer. Every car in the pits represents the cutting edge of what the big three automakers can produce when they pour their resources into going fast in a straight line. Then, this unassuming white Vega rolls off its trailer. The car looks normal enough from the outside, maybe a little plain compared to the flashy paint jobs on the factory cars. Bill Jenkins climbs out, walks around the car, checks the tire pressures, and doesn't say much to anyone. That is just who he is. Quiet, methodical, almost professorial. The other racers glance over but don't think much of it. Jenkins has been fast before, sure, but everyone figures they have caught up by now. But when that Vega fires up and makes its first pass, something bizarre happens. The entire chassis visibly twists during the launch. The body panels ripple like someone is squeezing the car from both ends. The rear of the car squats so hard it looks broken, like the frame just gave up and collapsed. The front end lifts higher than any pro stock car anyone has ever seen, and then it just hooks and goes, hard. Other racers are literally laughing in the pits. A few crew chiefs walk over to get a closer look, shaking their heads. Jenkins finally lost it, they whisper to each other. That chassis is junk. Look at how it moves. There is no way that thing is going to hold together for a full race day. Someone is going to get hurt. And then they see the time slips. 1.05 seconds into 60 foot. In 1974, that was physically impossible. The best rigid chassis cars in the class were struggling to break 1.15 seconds. Jenkins was not just a little faster, he was a full 10th quicker in the first 60 feet, which in pro stock drag racing is an absolute eternity. He was not just winning, he was rewriting the physics book. And that is the story we're going to tell today, how Bill "Grumpy" Jenkins outsmarted General Motors, violated every principle of chassis design that the automotive industry held sacred, and revolutionized drag racing with a Vega that bent on purpose. Now, to understand why Jenkins's flexible chassis was so revolutionary, you really need to understand what everyone else was doing in 1974. Here's the thing. The pro stock class was only about 3 years old at that point, having been formally introduced by the NHRA in 1970. But in those 3 short years, it had already become the most technologically advanced form of door slammer drag racing in the world. These were not your buddy's street car with slicks and a roll cage bolted in. By 1974, pro stock had evolved into purpose-built race cars that only looked like production vehicles from the outside. Under those factory-appearing bodies were full-tube chassis, fabricated from 1430 chromoly steel tubing, and they were designed with one overriding philosophy: be as rigid as humanly possible. The conventional wisdom was simple, and it seems completely logical if you did not think too deeply about it. A rigid chassis provided consistency. Every launch would be identical because the chassis was not introducing any variables. The suspension geometry would not change under load because the mounting points were locked in place. The engine would not twist in the mount because the frame rails held everything perfectly aligned. The rear end housing would stay square to the chassis because there was no flex to knock it out of position. Everything was predictable, repeatable, and controllable. Or at least that was the theory. Chrysler's Direct Connection Racing Manual, which was basically the Bible for anyone campaigning a Mopar in competition, explicitly stated that chassis flex was the enemy of performance. They printed it right there in black and white, underlined it, and probably would have put it in flashing neon if they could have figured out how to do that on a printed page. General Motors' racing division published technical papers showing that torsional rigidity was directly proportional to elapsed times. The stiffer your chassis, the faster you went. Period. End of discussion. Ford's chassis specifications for their factory-supported teams called for deflection rates under 500 pounds per inch. If your chassis flexed more than that, Ford's engineers said you were doing it wrong and they would not help you anymore. Everyone agreed. Every engineer, every chassis builder, every crew chief, every driver. Stiffer was better. And on the surface, the numbers seem to back this up perfectly. The top Pro Stock cars of 1973 all featured heavily triangulated chassis designs, with torsional rigidity exceeding 8,000 pound-feet per degree. That is an incredibly stiff structure. To put it in perspective, a typical production car of that era had torsional rigidity of maybe 2,000 pound-feet per degree. These race cars were 4 times stiffer than anything you could buy from a showroom floor. Bob Glidden's Ford Pinto used a ladder bar rear suspension with 12 separate attachment points, each one reinforced with gussets and braces until the rear of that chassis looked like a steel spiderweb. Ronnie Sox and Buddy Martin's Plymouth Duster featured a proprietary 4-link design with spherical rod and bearings rated for 30,000 pounds of load. These were aerospace-grade components, the same kind of hardware you would find holding together fighter jet landing gear. The cars were essentially rigid cages wrapped in fiberglass body panels that were shaped to look like something you could buy at a dealership. But here is what most people do not realize. There was a problem that nobody wanted to talk about. Despite all this rigidity, despite the massive rear slicks, despite the perfect suspension geometry, despite the factory engineering support and the unlimited budgets, Pro Stock cars could not hook up. Not really. Not consistently. The class had hit a wall, and the wall was made of tire smoke. By 1974, the engines in these cars were producing over 650 horsepower from naturally aspirated small block engines. The cars weighed just 2,350 pounds with the driver. Do the math on that power-to-weight ratio, and you will see the problem immediately. These cars had way more power than the available traction could handle. The best 60-foot times in the class hovered around 1.18 seconds, and breaking into the 1.15 range was considered exceptional. Only a handful of drivers could do it consistently, and even they admitted it was more art than science. The cars would either blow the tires off in a cloud of white smoke, or the crew chief would dial back the launch RPM so far that the car bogged down, sacrificing reaction time and early acceleration trying to control wheel spin. It was a frustrating paradox. You could build more power, but you could not use it. You could bolt on bigger tires, but the rules limited tire size. You could add more weight to the rear, but minimum weight rules and weight distribution percentages were strictly enforced. Everyone was stuck. And everyone was looking for the answer in the same places. Better tires, better clutch management, better track preparation. Everyone except Bill Jenkins. Jenkins saw what everyone else missed. The problem was not too little chassis rigidity. It was too much. And look, Jenkins was not your typical drag racer, not by a long shot. While other Pro Stock competitors came from mechanical backgrounds, former mechanics, engine builders, fabricators, guys who learned their trade by getting their hands dirty and figuring things out through trial and error, Jenkins held a degree in mechanical engineering from Cornell University. Let that sink in for a moment. This was a guy who could derive differential equations in his sleep, who understood material science and structural dynamics at a level that most race car builders cannot even conceptualize, let alone apply. He had worked as a project engineer at General Motors before going independent in 1965, so he knew exactly how the factory engineers thought, what their assumptions were, and more importantly, where those assumptions might be wrong. His shop in Malvern, Pennsylvania had become legendary for building winning combinations, but what most people did not see was the method behind the madness. Jenkins approached racing like a scientist, not a mechanic. He kept detailed logs of every single run he ever made, not just elapsed time and speed, but weather conditions, track temperature, barometric pressure, density altitude, relative humidity, wind speed and direction. He recorded suspension measurements before and after every pass. He logged tire pressure data, shock absorber dynographs, clutch engagement profiles, engine RPM curves. His shop looked more like a laboratory than a garage. There were filing cabinets full of notebooks, each one meticulously organized by date and event. In late 1973, Jenkins started doing something that nobody else in Pro Stock was doing. He began analyzing high-speed film of Pro Stock launches. He set up a 16mm camera at the starting line and filmed every car he could, including his own. Then he took that film back to his shop and went through it frame by frame, measuring how weight transferred from front to rear during the launch sequence. He used reference points on the cars and known dimensions to calculate actual deflection angles and displacement distances. What he discovered contradicted everything the chassis builders and factory engineers believed. The rigid chassis cars were not transferring weight efficiently. They were fighting themselves. And this is where it gets really interesting, because what Jenkins figured out was so counterintuitive that even after he proved it worked, people still had trouble wrapping their heads around it. Here is what was actually happening during a Pro Stock launch. When the car leaves the starting line, the rear tires try to drive the car forward while the front of the car wants to stay put due to inertia. This creates a rotational force around the rear axle center line that tries to lift the front end and plant the rear. This is basic physics, and everyone understood it. But in a perfectly rigid chassis, this rotational force has to overcome the entire mass of the car instantaneously. There's no give, no compliance, no progressive loading. The rear suspension compresses because the springs and shocks allow it to, but the chassis itself does not help with the weight transfer at all. It just sits there like a steel bridge, refusing to participate. Jenkins used an analogy that was brilliant in its simplicity. He said it is like trying to lift a steel beam versus a rope. If you grab one end of a steel beam and try to lift it, you have to overcome the weight of the entire beam all at once. The beam resists uniformly along its entire length. But if you grab one end of a rope and lift, the rope conforms to the force. The end you are holding comes up first, then the middle follows, then the far end. The total weight is the same, but the force required at any given instant is much less because you are lifting it progressively, not all at once. Jenkins calculated that if the chassis could flex in a controlled manner during the first 60 feet, it would actually help transfer weight to the rear tires. The front end would rise more easily because the chassis was not fighting the rotational force. The rear would squat harder because more of the car's mass was being directed downward onto the rear axle. And critically, this weight transfer would happen progressively, not all at once, keeping the rear tires in their optimal traction window instead of shock loading them with a sudden spike of force that would break them loose. But this idea flew directly in the face of everything racers believed. A flexible chassis meant inconsistency, they said. It meant unpredictability. It meant weakness. It meant danger. Jenkins heard all of these objections and addressed each one with data. Inconsistency? He showed mathematically that a controlled flex chassis would actually be more consistent because it would self-adjust to varying track conditions. Unpredictability? He demonstrated that the flex could be engineered to follow a precise and repeatable deflection curve. Weakness? He calculated that the distributed loads in a flex chassis would actually result in lower peak stresses than a rigid design. Danger? He proved that the flex zones would act as crumple zones in a crash, absorbing energy progressively rather than transmitting it directly to the driver. Nobody bought it. Not one person. Jenkins did not care. He spent the entire winter of 1973 into 1974 redesigning his Vega chassis with calculated flex zones. And I want to emphasize this point because it is crucial to understanding what Jenkins did. This was not random weakening. He did not just take a hacksaw to his frame rails and hope for the best. This was precision engineering, the kind of work that would earn a graduate thesis at any major university. Every modification was calculated, tested, and verified before it went on the car. The main frame rails were 2-inch by 3-inch rectangular tubing with 0.095-inch wall thickness. That is 40% thinner than the standard wall thickness used by every other chassis builder in Pro Stock. When other builders heard about this, they were genuinely alarmed. They thought Jenkins was building a death trap. But here is where it gets clever, and this is the part that separates Jenkins from someone who just got lucky. Jenkins did not make the entire chassis flexible. He created specific flex zones with carefully calculated stiffness transitions between them. The front section of the chassis, from the firewall forward, remained fully rigid. He used traditional triangulation with diagonal bracing, gussets at every joint, and heavy wall tubing. This section held the engine, the steering, and the front suspension. It needed to be stiff because any flex here would affect engine alignment and steering precision. The rear section, from the rear door posts back to the tail, was also rigid. Heavy cross members, diagonal bracing, reinforced shock mounts, and thick wall tubing. This section held the rear axle, the suspension pickup points, and the fuel cell. It needed to be stiff because the rear suspension geometry had to remain precise. But the middle section, from the firewall to the rear doorposts, that is where the magic happened. Jenkins eliminated the diagonal bracing entirely in this area. He used single cross members instead of the doubled cross members that every other builder used. He even cut small relief notches in non-critical areas of the tubing to encourage controlled flex along specific axes. He was essentially turning the middle of the chassis into a large torsion bar, a spring that could twist under load and return to its original shape when the load was removed. The engineering behind this was brilliant in its sophistication. Under launch loads, the chassis would twist approximately 2.3 degrees from its static position. Now you might be thinking, 2.3 degrees, that is nothing, who cares? But in the context of weight transfer physics, that small twist had enormous consequences. That controlled twist allowed the front end to rise more easily, reducing the force needed to initiate weight transfer. Simultaneously, the rear of the chassis squatted harder because the twist was directing more of the car's mass downward and rearward. The chassis was essentially acting as a torsion bar, storing energy during the initial hit of the clutch and releasing it progressively as the car accelerated through first gear. Jenkins calculated that this flex increased rear tire loading by approximately 340 pounds during the critical first 20 feet of the run. 340 pounds might not sound like much on a 2,350-pound car, but at the tire contact patch, it was the difference between hooking and spinning. It was the difference between a 1.15 60-foot time and a 1.05. But the real genius, the part that truly separated Jenkins from a mad scientist, was in the control. Jenkins did not want the chassis flexing randomly or unpredictably. He installed adjustable limiting straps made from aircraft-grade webbing material that controlled the maximum deflection the chassis could achieve. These straps could be lengthened or shortened to tune the amount of flex for different track conditions. On a well-prepared, sticky track, he would shorten the straps to limit flex because the tires did not need as much help hooking up. On a marginal or cold track, he would lengthen them to allow more flex and more progressive weight transfer. He used specially valved shock absorbers that did not just control suspension movement, but actually dampened the chassis flex rate. The shocks were mounted at specific angles to resist torsional movement in the chassis, acting as dampers for the entire structure, not just the suspension. He even positioned the battery and the fuel cell at calculated locations to create the optimal center of gravity position during the flex cycle. When the chassis twisted, the battery and fuel cell would shift slightly, and Jenkins had calculated exactly where they needed to be so that this shift would enhance the weight transfer rather than fight it. Every single component on the car was positioned to work with the chassis flex, not against it. Nothing was there by accident. Nothing was left to chance. The first real test came in February of 1974 at Gainesville Raceway in Florida during pre-season testing. Jenkins unloaded his white Vega, the car his crew had nicknamed Grumpy's Toy, and immediately drew stares from the other teams. When he fired it up and rolled to the burnout area, other racers noticed something odd about the car. It seemed to squat differently when he did his burnout. The rear quarter panels visibly flexed in and out as the tire spun. The hood twisted slightly when he brought the RPMs up. It looked wrong. It looked broken. It looked like the car was going to come apart at any moment. A few crew chiefs from other teams actually walked over and suggested to Jenkins that he might want to check his chassis for cracks. Jenkins just smiled that thin little smile he was famous for and said nothing. His first full pass shocked everyone in the building, including Jenkins himself if he was being honest about it later. The car left the starting line with a 1.08 second 60-foot time and ran 8.86 at 152 miles per hour. For context, the NHRA Pro Stock national record at that time was 8.83. On his very first test pass with an experimental chassis that everyone said would not work, Jenkins was within 0.03 of a second of the national record. The other teams stopped laughing. By the end of that test day, Jenkins had made 6 more passes. His best run was an 8.81 at 154 miles per hour with a 60-foot time of 0.105 seconds. He had broken the national record unofficially since it was a test session and not a sanctioned event. But the numbers were real, the timing system was certified, and there were dozens of witnesses. The improvement was not just in the raw 60-foot times either. The flexible chassis made the car dramatically more consistent from run to run. Where the rigid chassis cars in Pro Stock would typically vary by 2 or 3/100ths of a second depending on slight changes in track conditions, air temperature, or humidity, Jenkins's Vega was repeating within 5/1000ths of a second. 5/1000ths! That kind of consistency was unheard of in 1974. The controlled flex was adapting to different track surfaces automatically, just as Jenkins had predicted in his calculations. On a good, well-prepared track surface, the chassis would flex less because the tires hooked up more quickly and the rotational forces were lower. On a marginal track surface, the chassis would flex more because the tires needed more time and more progressive loading to find traction. The car was essentially self-adjusting without anyone turning a single knob or changing a single setting. It was brilliant. Word spread through the Pro Stock community faster than one of Jenkins's quarter-mile passes. By the time the 1974 NHRA Gator Nationals rolled around in March, every team in the pits was talking about Jenkins and his weird flexi Vega. Some people still thought he was crazy. Others were starting to pay very close attention. Jenkins qualified number 1 at the Gator Nationals with an 8.78 at 155 miles per hour. That was not just quick, that was otherworldly for 1974 Pro Stock. In eliminations, he was absolutely devastating. First round, Jenkins runs 8.80, his opponent runs 8.94. It was not even close. Second round, Jenkins runs 8.79, his opponent manages 8.91. Still not close. Semifinals, Jenkins clicks off an 8.78 while his opponent struggles to an 8.85. And in the final round against Bob Glidden, who was no slouch and would go on to become one of the greatest Pro Stock racers in history, Jenkins ran an 8.77 at 154 miles per hour for the event win. Glidden, running one of the best rigid chassis cars in the class, could only manage an 8.89. Jenkins had just won the biggest Pro Stock race of the young season, and he had done it with a chassis that every expert in the sport said was fundamentally wrong. The technical press went absolutely crazy. Hot Rod magazine sent a photographer and a technical editor to Jenkins's shop to document the chassis in detail. They crawled under the car, took measurements, photographed every joint and every crossmember. Their article ran 6 pages and still could not fully explain what Jenkins had done. Superstock and Drag Illustrated published a 3-part series trying to break down the flex theory for their readers. The editors admitted they had to consult with structural engineers outside of motorsports to even understand the principles Jenkins was applying. Carcraft magazine went even further. They actually commissioned a replica chassis to test Jenkins's concepts independently. They built 2 identical Vega frames, one rigid and one with Jenkins-style flex zones, and tested them back-to-back on the same car with the same engine and the same driver. What they found defied everything the conventional racing wisdom had taught them, but it proved Jenkins right on every single point. The key insight that the Carcraft test revealed was something Jenkins called resonant frequency matching. This is where it gets really technical, but stay with me because this is the part that truly shows how far ahead of his time Jenkins was thinking. Every chassis, every structure really, has a natural resonant frequency. That is the rate at which it wants to oscillate when disturbed. Think of it like a tuning fork. Strike a tuning fork and it vibrates at a specific frequency determined by its size, shape, and material. A chassis works the same way. Most rigid Pro Stock chassis of that era had natural resonant frequencies around 180 Hz. That means they wanted to vibrate back and forth 180 times per second. Now here's the critical part. The launch event, the actual moment when the car leaves the starting line under full power, happens at a frequency of approximately 2 Hz. That is the rate at which the weight transfer occurs, the rate at which the forces build and release during the launch cycle. 180 Hz versus 2 Hz. That is a massive mismatch. And when you have a mismatch like that between the driving force frequency and the structural natural frequency, the structure fights the force. It resists it. It does not want to move at 2 Hz because it wants to move at 180 Hz. The energy gets wasted in vibration and heat instead of being directed into weight transfer and traction. Jenkins's flexible chassis design had a natural frequency of approximately 8 Hz. That is still not a perfect match with the 2 Hz launch frequency, but it is dramatically closer than 180 Hz. And because it was closer, the chassis worked with the launch forces instead of against them. It moved in harmony with the weight transfer rather than fighting it. The flexible chassis also solved another problem that had been plaguing Pro Stock for years: tire shake. When a drag slick breaks loose from the track surface and then regains traction rapidly, it creates a violent oscillation that shakes the entire car. In a rigid chassis, this shake transfers directly through the structure to every component. It rattles the engine and its mounts, shakes the transmission, vibrates the drive shaft, unsettles the driver, and often damages parts or breaks things. Many Pro Stock runs were lost because of tire shake. The car would hook, shake, and the driver would have to lift off the throttle to keep from destroying something. Jenkins's flexible chassis absorbed these oscillations the same way a shock absorber handles a bump. The flex zones acted as structural dampers, soaking up the violent energy of tire shake before it could propagate through the rest of the car. The result was that Jenkins could drive through tire shake that would sideline rigid chassis cars. Where other drivers had to lift, Jenkins just kept his foot in it and let the chassis deal with the problem. Now, you might be thinking this all sounds too good to be true. And initially, General Motors' own engineers agreed with you. When GM's racing division first heard about what Jenkins was doing with their Vega, they were not impressed. Internal memos from GM's competition department called Jenkins's design theoretically unsound and predicted it was unlikely to produce results and likely to result in catastrophic structural failure. They were so convinced Jenkins was wrong that they sent a team of 4 engineers to the 1974 NHRA Spring Nationals specifically to study his car and document its inevitable failure. What those engineers found changed everything GM thought they knew about chassis design. The GM engineering team used strain gauges bonded to critical points on Jenkins' chassis, triaxle accelerometers mounted at the rear axle on the driver's seat, and high-speed cameras running at 500 frames per second. They collected data on 6 of Jenkins's runs over the course of the event weekend. Their analysis revealed something remarkable that none of them had predicted. During launch, a conventional rigid Pro Stock chassis experienced stress concentrations exceeding 85,000 pounds per square inch at the primary mounting points. That is dangerously close to the yield strength of 4130 chromoly steel, which means the rigid chassis cars were actually closer to structural failure than Jenkins's flexible design. Jenkins's chassis never exceeded 45,000 psi anywhere in the structure. The flex was distributing the loads more evenly across a larger area of the chassis, effectively making it stronger under racing conditions, not weaker, the opposite of what everyone had assumed. The accelerometer data was even more revealing. Rigid chassis cars showed vertical acceleration spikes of 4.2 Gs at the rear tires during the launch event. That is the force slamming down on the tires at the moment of launch. Jenkins's car showed 2.8 Gs. Lower peak acceleration meant the tires were less likely to be shock-loaded past their traction limit. But here is the part that really made the GM engineers sit up in their chairs. The overall weight transfer, the total amount of load that moved from the front tires to the rear tires during the launch, was actually greater with the flexible chassis. Jenkins's car transferred more weight, but it did it more smoothly and progressively, keeping the rear tires in their optimal traction window throughout the entire launch sequence, instead of spiking past the traction limit and then dropping back below it. GM's final report on their investigation concluded that Jenkins had, and this is a direct quote from the documents, revolutionized understanding of chassis dynamics in drag racing applications. Coming from the same company that had called his work theoretically unsound just months earlier, that was quite an admission. They immediately began developing their own flexible chassis designs for factory-backed teams. Within 6 months of that report being circulated, every major Pro Stock competitor was experimenting with some form of controlled chassis flex. The variations that other teams came up with were fascinating in their own right. Ronnie Sachs and Buddy Martin developed what they called a beam pivot design, where the main frame rails could rotate around the central pivot point located near the center of gravity. Bob Glidden created what he termed a torsional cell chassis, using hollow rectangular sections with specific wall thicknesses that could twist predictably along their length. Don Nicholson, always an innovator, built what he called a harmonic flex design, with different wall thicknesses at different points along the frame rails, creating multiple resonant frequencies that could be tuned independently. But every single one of these designs was chasing the breakthrough that Jenkins had made first. They were all variations on his theme. The impact on Pro Stock performance was immediate and dramatic. By the end of the 1974 season, the NHRA Pro Stock national elapsed time record had dropped from 8.83 to 8.68. 60-foot times that had been stuck at 1.15 for what felt like forever suddenly plummeted below 1.10. Jenkins himself reset the national record 4 times during the 1974 season, ultimately running 8.63 at 157.21 miles per hour. More importantly, the cars became easier to drive. The controlled flex made them more forgiving of imperfect track conditions, more consistent from run to run, and more predictable in how they responded to driver inputs. This was not just about going faster, it was about making speed accessible. Jenkins did not stop innovating after that first season. For 1975, he developed what he called active flex control, and this is where the story moves from impressive to almost unbelievable. The active flex system used hydraulic cylinders mounted at the flex zones to adjust the chassis stiffness while the car was running. Sensors measured wheel speed, drive shaft speed, and longitudinal G-forces. A simple analog computer, really just an arrangement of potentiometers and operational amplifiers mounted in a small aluminum box, calculated the optimal flex rate for the current conditions and adjusted the hydraulic pressure accordingly. The system could stiffen the chassis for high-speed stability in the top half of the track, and then soften it automatically for the next launch. It could even adjust side-to-side flex to compensate for crosswinds or an uneven track surface. In testing, the active system improved 60-foot times by another 0.02 of a second and added 2 miles per hour to trap speeds. But NHRA banned the system before Jenkins could ever race it in competition. They classified it as an electronic driving aid, which was prohibited under Pro Stock rules. The irony was rich. The system was not electronic at all. It was hydraulic with analog controls. There was not a single transistor or microchip anywhere in it. But NHRA was not ready for that level of sophistication in 1975. And honestly, you can understand their concern. If they allowed active chassis control, where would it end? Jenkins was philosophical about the ban. He said he expected it and had the system ready primarily as a proof of concept for future development. He was thinking 10, 20 years ahead of the sanctioning body. The flexible chassis concept did not stay confined to Pro Stock. Top Fuel dragster teams started experimenting with controlled flex in their 300-inch wheelbase rail chassis. Funny car builders incorporated flex zones between the carbon fiber driver compartment and the rear engine mounting structure. Even pro-modified cars, those wild tube chassis machines with centrifugal superchargers and nitrous oxide, adopted flexible subframes based on Jenkins principles. The entire sport of drag racing had been transformed by one man's willingness to question what everybody else accepted as gospel truth. The real validation of Jenkins's work came from an unexpected source entirely outside of motorsports. In 1976, Chrysler's aerospace division was contracted by the United States Department of Defense to design a new transporter-erector launcher for mobile missile systems. The requirements called for a vehicle that could maintain stability while carrying a 40,000-pound ballistic missile over rough terrain at speeds up to 50 miles per hour. The preliminary designs all featured massive, rigid chassis structures with complex multi-link suspension systems and active stabilization platforms. The projected cost was enormous, and the weight was prohibitive. Then, someone in the engineering department remembered reading about Jenkins's flexible Vega in a technical journal. Chrysler's aerospace engineers applied Jenkins's controlled flex principles to the missile transporter chassis. Instead of fighting rough terrain with the rigidity and brute strength, they designed the chassis that could flex predictably, absorbing impacts and terrain irregularities while maintaining load stability through progressive compliance rather than absolute resistance. The prototype exceeded every single requirement in the specification. It was lighter than the rigid design, cheaper to manufacture, easier to maintain, and more reliable in field testing. The project led to a multi-million-dollar military contract that kept Chrysler's defense division profitable for years. The official engineering report credited drag racing innovation, specifically citing Jenkins's flexible chassis theory as the foundational concept. A Chevy Vega drag car helped design a missile launcher. You cannot make this stuff up. Jenkins himself was characteristically philosophical about his innovation. In a 1976 interview with National Dragster magazine, he said something that has stuck with me ever since I first read it. He said, "While everyone was trying to eliminate chassis flex, I just asked, what if we use it instead?" Racing is not about following rules. It is about questioning them. Every breakthrough comes from someone willing to look stupid until they prove everyone else wrong. That quote belongs in a frame on the wall of every engineering school in the country. The numbers tell the final story better than any words can. Before Jenkins's flexible chassis, Pro Stock cars struggled to run in the 8.80 range. Within 2 years of his innovation, the class record stood at 8.48. 60-foot times dropped from 1.15 to 1.02. But the numbers do not capture the most important change. The class became more competitive across the board. The controlled flex technology made the cars easier to tune, more forgiving to drive, and more consistent from run to run regardless of conditions. It democratized performance. You no longer needed a factory contract and unlimited resources to be competitive. You needed understanding of the principles, and thanks to Jenkins's willingness to share his knowledge openly, those principles were available to anyone who wanted to learn them. Jenkins's flexible Vega won 13 national events between 1974 and 1976. He captured the 1974 NHRA Pro Stock Championship outright and finished second in 1975, losing the title by just a handful of points. But his real victory was not measured in trophies or championships. It was measured in changed minds and transformed approaches. He proved that sometimes the solution to a problem is not to fight harder against the obstacle, but to work with it more intelligently. He showed that the answer was not always more, sometimes it was different. Today, every single Pro Stock car that rolls into the staging lanes uses controlled chassis flex. Modern chassis builders use finite element analysis software to map flex patterns with precision that Jenkins could only dream of with his slide rules and hand calculations. They employ exotic materials like carbon fiber composites and titanium alloys to create precise flex zones with specific stiffness profiles. Computer simulations optimize every tube placement, every gusset angle, every wall thickness for perfect controlled deflection under every conceivable loading condition. But they are all following the path that Bill Jenkins blazed with his weird, flexy, too thin Vega chassis back in 1974. The current NHRA Pro Stock record stands at 6.43 seconds at 213 miles per hour. These modern cars generate over 1,500 horsepower from naturally aspirated engines and pull nearly 6 Gs on launch. They achieve 60 foot climbs under 0.97 seconds. None of this, not a single tenth of a second of it, would be possible with rigid chassis designs. The controlled flex that Jenkins pioneered is what allows these cars to hook up and accelerate harder than physics should reasonably allow. The lesson here extends far beyond drag racing, and it is a lesson worth remembering. Jenkins showed that questioning fundamental assumptions, even ones that everyone agrees on, even ones backed by factory engineers and published data and decades of experience, can lead to breakthrough innovations that change everything. He proved that sometimes the wrong answer is actually the right answer. You just have to understand the problem deeply enough to see why. He demonstrated that engineering is not about blindly following formulas and accepted practices. It is about understanding the underlying principles so thoroughly that you know when to break the rules and why breaking them will work. Consider what Jenkins was up against. General Motors, with effectively unlimited engineering resources and armies of degreed engineers, said he was wrong. The entire pro stock racing community, filled with successful competitors and experienced chassis builders who had decades of combined experience, said rigid was right and flex was dangerous. Automotive engineering textbooks going back to the beginning of the automobile preached the gospel of chassis stiffness as an absolute good. But Jenkins had something more powerful than consensus. He had data, he had curiosity, and he had the courage to trust his own calculations over conventional wisdom, even when every voice around him said he was making a mistake. In 2012, Jenkins was inducted into the International Drag Racing Hall of Fame. The citation specifically mentioned his revolutionary flexible chassis design that transformed pro stock racing and influenced chassis engineering across all forms of motorsport. At the ceremony, Jenkins, then 81 years old, stood at a whiteboard and demonstrated his original calculations, walking the audience through the mathematics of how he had derived the optimal flex rates and resonant frequencies for that first Vega chassis. The audience, a room full of engineers, racers, and motorsport professionals, gave him a 5-minute standing ovation. Jenkins passed away later that same year, but his influence continues every single day in every form of motorsport. Every time a pro stock car launches from the starting line, flexing and twisting as it rockets down the quarter mile, it is validating his vision. Every 0.96 second 60-foot time is a testament to his willingness to question what everyone else accepted without question. Every championship won by a car with controlled chassis flex is part of his enduring legacy. The story of Bill Jenkins and his flexible Vega chassis is more than just a fascinating chapter in racing history. It is a reminder that innovation almost always comes from questioning what everyone knows to be true. It is proof that one person armed with calculations and courage can outsmart entire corporations with unlimited budgets. It is evidence that sometimes the best solution is the one that looks completely wrong to everyone else watching. Racing has always been about going faster than the other guy, but Jenkins showed us it is also about thinking differently than the other guy. While they built stronger, he built smarter. While they added rigidity, he added intelligence. While they fought physics with brute force, he made physics his most valuable ally. That white Vega with the weird chassis that flexed on purpose, the car that made veteran racers laugh and factory engineers shake their heads, it did not just win races, it changed racing forever. And it all started with one quiet engineer in Pennsylvania who was willing to ask the simplest and most dangerous question in all of science and engineering. What if everyone else is wrong? So what is the most counterintuitive modification you have ever seen actually work? Drop a comment below and let me know. I want to hear your stories about the times when the wrong answer turned out to be exactly right. And if you enjoyed this deep dive into the drag racing innovation that changed everything, make sure to subscribe because we are just getting started exploring the engineering marvels that transformed motorsports. Until next time, keep questioning the obvious. I'll see you at the track.